In a system of equations, whether the equations are linear or nonlinear, the solution is going to be an ordered pair xy that satisfies both equations. And one way to find that solution is to graph the two equations and look for the intersection point or points. So if we're going to apply that approach, that's what we call solving graphically, then we first need to get prepared to think about each of these equations individually. Y equals x minus 2 squared is a quadratic function, and it is written in vertex form so we can see the transformations. This is just one transformation of y equals x squared, which is a shift right 2. So starting from y equals x squared, which is a parabola with vertex at the origin, I would move right to put that vertex at 2, 0, and then use my same shape that I know for y equals x squared to draw in this graph. Looks like our grid here goes out 8, so this next point would be just a little bit off. So that gives me y equals x minus 2 quantity squared. The other graph I'm going to draw is x plus y equals 4, which is linear. And there's a couple of ways I could do this. I could either put it in slope-intercept form by subtracting off the x, and then draw a line with y-intercept 0, 4, and slope -1, so that I would think of as a fraction -1 over 1. Or I could do this using x and y intercepts. Either way, this is the graph that I get. I can see from this example that I do have two solutions. One of them is here at 0, 4. The other one is here at what appears to be 3, 1. Because the context is ordered pairs and the original equations have both x and y, my solution set is going to have ordered pairs. So 0, 4 is the first ordered pair, and 3, 1 is the second. In either order, I can put both of these ordered pairs. Let's now take a look at how we would solve the same system of equations symbolically. Symbolically means we're not going to draw a graph, we're going to do an approach that involves just the symbols. Substitution is usually the easiest method to use for nonlinear systems of equations. And in this particular case, the first equation is already solved for y. Because of that, it seems like it will be easy to take this expression and plug it into the other equation where I have y. So the way I substitute is I solve one equation for a variable, and then I substitute that expression into the other equation. So I have x plus, and then the y that I'm replacing with x minus 2 quantity squared, and then going back to my original equation, I get equals 4. This is a quadratic equation, so I'm going to attempt to solve it by factoring. That gets me x plus squaring out this binomial. Remember, that's 3 terms, x squared minus 4x plus 4 equals 4. I can now subtract 4 from both sides in order to move terms all to the same side, and I can also combine these two like terms, x and minus x, all in one step. So that gets me this x squared The combined x terms give me negative 3x. The plus 4 and minus 4 actually drop out from both sides. That was coincidental. And this whole thing is equal to 0. This is a really easy GCF factoring problem. All I do is factor out x and I'm done. So setting each factor equal to 0 gets me 2 solutions. But note that these are both x values. So these are not coordinates of the same ordered pair. These are 2 different x values, and for each of them I now have to find a y. So I want to keep them separate so that when I find my y, I know which x it went with. I can at this point take either of the original equations. Very often the one that's already solved for y is easier, but in this case I might prefer the second equation, x plus y equals 4, just because it's linear and therefore a little bit simpler. So if x plus y is equal to 4 and x is 0, that gets me 0 plus y equals 4, and therefore y equals 4. So my ordered pair would be 0, 4. Over here on the right hand side, I've got the same x plus y equals 4. This time I am plugging 3 in for x. So subtracting 3 from both sides gets me y equals 1, and therefore the ordered pair 3, 1 comes from this equation. So I have 2 solutions. One is the ordered pair 0, 4. One is the ordered pair 3, 1. Fairly simple process. Just make sure that you remember that the first solutions you get are both for the same variable. When we were at this stage, we had an x and another x. We can't put those together into an ordered pair 0, 3, for example. These are 2 x's. Each of them needs a y, so we need to go through this back substitution process 2 times in order to get our solution. If we look back at our graphing example, we'll see that we do have the same 2 ordered pairs, 0, 4 and 3, 1, and back up here 0, 4 and 3, 1.